section 3.4, velocity and other rates of change. What we'll be learning about today are instantaneous rates of change, which we've already talked about, but today we'll look at some applications in the form of velocity, position, and acceleration. We'll also look at a quick look at economics, how they use instantaneous rates of change in economics as well. We'll be looking at motion along a line and a quick look at sensitivity to change. So we start off today again with the same concept we've been looking at for a few sections, and that is the instantaneous rate of change. So what we have here is the definition of instantaneous rate of change, which we know is the derivative. And the definition we have given here is the definition at a point, and that point is at x equals a. So we take the limit as h approaches 0 of f of a plus h minus f of a all over h. I highlighted this next little passage from the book because it is a convention in this book, and we should be aware of it when they ask questions in this book that we answer correctly. It's a convention to use the word instantaneous even when x does not represent time. The word, however, is frequently omitted in practice. When we say rate of change, we mean instantaneous rate of change. So that is a convention for this book. And when we look for average rate of change, that will be clearly stated, average rate of change. So if it says simply rate of change, you are to assume instantaneous, which means we are taking the limit of the average rate of change. All right, let's move forward to our first example. And we actually have had a problem like this in one of our quizzes or tests already, but let's go ahead and take a look at it. It's enlarging circles. Find the rate of change of the area of a circle with respect to its radius r. Let's start with that. If we are working with area of a circle, we need to remember that area is pi r squared. And if we are taking the derivative, or the rate of change, of area of a circle with respect to its radius, then immediately we should ask ourselves, what are we trying to solve for? And if we want the rate of change of area, then the easiest notation that is useful in application problems for me is this Leibniz form of the derivative, dA dr. That says I am taking the derivative of area with respect to radius. So that tells us our variable is the radius, r. Everything else can be considered a constant in this example. So we take the derivative of a with respect to r. Pi is a constant. So we bring our 2 down using power rule, and we have 2 pi r for our derivative. And now in part B, we are asked to evaluate this rate of change at r equals 5 and r equals 10. So let's take a look at that. We simply plug in r equals 5 into our derivative or rate of change function, instantaneous rate of change function, and we have 2 pi times 5 and 2 pi times 10, giving us 10 pi and 20 pi. Part C then says if r is measured in inches and a is measured in square inches, what units would be appropriate for dA dr. This is the other thing that's nice about using the dA dr notation, because it makes clear to you I am doing area, change in area over change in radius. Well, area is measured in inches squared in this case, and radius is measured in inches. So our units then are inches squared over inches. And you can leave it that way, or you could write it simply as inches when they cancel. It might be more useful in this case to just leave it as inches squared over inches, so you can see rate of change of area over rate of change of radius. All right, and that is example 1. Let's go ahead and move on. And the next thing we're going to be talking about is motion along a line. So we're talking about horizontal movement, okay? So we have a position graph here in one dimension where the horizontal axis represents position S. And our position at time t is marked here with our first blue dot, and we'd say S is our function f of t. And at a time t plus delta t, we're now over here on our position line, and that would be S plus delta S, which could also be written as f of t plus delta t. So we're talking about movement on a horizontal line. So our first term that we need to clarify here is displacement over some time interval. It would be notated as delta S, and to get that displacement it would be f of t plus delta t minus f of t. So again, we're talking about that distance here from our original position. So that is how I want you to think of displacement, is how far I am from my original position. Alright, sorry for my lovely writing. My Moby board was left at school, so we're doing this on the computer. So, displacement, how far am I from my original position? Alright, and then we move on and we see how displacement is related to average velocity. The average velocity of an object over time is the displacement, f of t plus delta t, minus f of t, so just that change in position, over change in time. So displacement over travel time would give us average velocity. We will be talking about displacement versus total distance traveled, and we need to remember that if I start here at s equals f of t, and I go way off to the right and come back to this second blue dot, my total distance is far larger than my displacement. My displacement would be the same. I would still be this distance right here from my original position, and that would be my displacement, but my total distance traveled would be far more, and we'll talk about that in further examples. So now moving from average velocity to instantaneous velocity. The instantaneous velocity is the derivative of the position function s equals f of t with respect to time. Well, we have dealt with average rate of change versus instantaneous rate of change, and this is just in the realm of velocity. So our average velocity was f of t plus delta t minus f of t over delta t. And now we take the limit as that delta t goes to 0. So this is simply the derivative function with respect to position and time. We have dealt with the derivative function with f of x plus h minus f of x all over h. Same thing, but we're just setting it now in a position and time environment. Quite often you'll see position represented by an s function, so that's why velocity here is written as ds dt. And finally, before we look at some examples for this type of problem, we will also need to evaluate speed. And speed is related to velocity in that speed is the absolute value of velocity. So if you've dealt with physics at all, you know that speed has only a magnitude. Speed is a value. It is how fast we are going. It does not take into account direction. So velocity has a magnitude and a direction, and speed is a scalar and has only a magnitude. So if we find our velocity, then we can take the absolute value of that velocity to get our speed. Now let's go take a look at an example. So there is our speed definition. And we'll take a look at an example using a velocity graph. We need to be able to interpret all of these things we've just discussed graphically as well as numerically. So let's take a look at example 3, reading a velocity graph. It says a student walks around in front of a motion detector that records her velocity at 1-second intervals for 36 seconds. She stores the data in her graphing calculator and uses it to generate the time velocity graph shown in figure 3.25 right here. Describe her motion as a function of time by reading the velocity graph. When is her speed a maximum? So before we start breaking down what's going on this velocity graph, we see velocity is our y and time is our x. It looks like our intervals are 4 seconds out to time 36. All right, so from time 0 to time 4, 8, 12 seconds, our student is walking forward. I know this because my velocity graph is all above the x-axis, so her velocity is positive, so she is walking forward. And the other thing that we need to think about is in this section right here, the slope of this graph is positive, and that would mean that she is speeding up. So where the slope of a velocity graph is positive, our acceleration is positive. So the slope of the velocity curve is our acceleration, which means the derivative, the instantaneous rate of change of velocity, would be acceleration. So where the slope of the velocity curve is positive, and that means our acceleration is positive and our student is speeding up. Okay? And then from time 4 over to time 8, the velocity is constant, so our acceleration there would be 0. Then from time 8 to time 12, about time 12, it goes a little bit further, we are looking at a negative slope, so our acceleration there would be negative, and right here, just past 12, our velocity is 0, because from time 0 to this point, the student is walking forward. But right after this point right here, the student starts walking backward. So the velocities would be below the x-axis. Okay? All right, from about time 12, let's see, 16, 20, 24, let's say about 26. The student continues to walk backward between time 12 to time 26. And let's look at our acceleration here. Our acceleration here is negative, but our velocity is also negative. Our v of t is also negative in this section. If you can read that. And when our acceleration is negative and our velocity is negative, we would say that our student is speeding up in the negative direction. So they were speeding up while they were walking backward. Okay? And then in this section here, our acceleration is positive, but our velocity is still negative. So let me note that. Remember, the acceleration is the slope of this graph of velocity. So it's rising to the right, so my acceleration is positive, but my velocity, the y values of this graph, are plotted below the x-axis, so my velocity is negative. So we are still moving in the negative direction, but our acceleration is positive, so we are slowing down. What we see here is when acceleration and velocity have the same sign, we are speeding up, and when acceleration and velocity have opposite signs, we are slowing down. All right, so we have noted over here when acceleration is positive and velocity is positive, or when acceleration is negative and velocity is negative, we are speeding up. When they have opposite signs, acceleration positive, velocity negative, or velocity positive, acceleration negative, we are slowing down. Okay, so from time, what did we say, 26 through 32, it looks like we have no velocity at all. In this section, velocity is 0. And that would mean that the student stopped walking. There's no positive or negative velocity happening there. And then from 32 to 36, the student starts walking forward again with a positive acceleration. So in this section, velocity is positive and acceleration is positive, so the student is speeding up. Okay, so we've broken down this graph, and what we want to look at now, we want to answer the question that was posed to us. When is her speed a maximum? Remember, speed is the absolute value of velocity. So you consider the speed graph the same as this velocity graph, except anything that was below the x-axis would be reflected above the x-axis. And that would make it the speed graph. And if that is the case, then the maximum speed would happen right here at 4, 8, 12, 16, 20, at t equals 20, because that is where our velocity graph is furthest from the x-axis. So our max speed would happen here. We would happen to be going backward or in the negative direction, but our speed would be largest right there. Alright, please use this video when you are going over your homework, trying your homework, to help you analyze your velocity graphs. Something we need to get good at, so keep this in mind to come back and check it as you are doing your homework. Alright, let's move forward. Acceleration. So we've actually started talking about this already. We saw that on the velocity graph, acceleration was the slope of the velocity. Well, that means that if velocity is given as ds dt, then acceleration could be written as dv dt, which is the derivative of velocity with respect to time, or as the second derivative of position. The first derivative of position with respect to time is velocity, and then the second derivative of position with respect to time would be acceleration. Alright, our book also gives us just some models that you may have seen in physics as well, or in science. Free fall constants on the Earth, English units, the effective gravity is 32 feet per second squared, and the model for free fall would be s equals 1/2 times 32 t squared, or 16 t squared. And then if we use metric units, our effective gravity is 9.8 meters per second squared. That's the acceleration due to gravity. And then our model for free fall, we could find the position at any time by doing 4.9 t squared. Those will be useful in your homework as well. Let's see what we have next. Alright, example 4, modeling vertical motion. So here we want to take a model, in this case, of a rock. Let's see, a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second, about 109 miles per hour. It reaches a height of s equals 160 t minus 16 t squared feet after t seconds. So we have a position function, s of t. And now we want to address some questions about this. So let's take a look. Our position function, as we said, is 160 t minus 16 t squared. Our first question is, how high does the rock go? Alright, so I've gone and picked up our graph that models this situation. And that's what we have here on the left. And our function, 160t minus 16t squared, is a parabola. And we are looking for how high the rock will go. And that happens, it looks like, based on our graph, at t equals 5. But let's think about, this is a parabola. And we are looking for the maximum of that parabola. And as long as we have a nice smooth graph like this, the maximum will happen at our vertex. And if you think about the slope of the tangent line at our maximum, if I can sketch it in here, like that, there's our tangent line at the maximum, and the slope of that line will be 0. So really, when we're asked to find our maximum height, or how high the rock goes, we're looking for the maximum height, and that is when the slope of the tangent line to this curve is 0. Well, the slope of this curve at any point is going to be the rate of change of position with respect to time, or the velocity. So if we are looking for the maximum height, we are looking for when the velocity, which is the derivative of this graph, equals 0. Well, we said at the beginning of this section that the derivative of position is instantaneous velocity. So we take the derivative of this position function, 160t minus 16t squared, applying the power rule, and we get 160 minus 32t. And we want to find where that equals 0. So I've shown our math here to get when the velocity equals 0. That's not answering our question yet. The question is, how high does the rock go? Well, we have found when it will reach its maximum. So now we need to plug our t equals 5 seconds into our position function to see how high it actually went. So this is s of 5, and evaluated at 5, we get our position to be 400 feet. Now this matches perfectly with our graph of 160t minus 16t squared. You can see at t equals 5, we have our maximum height at 400. Of course, we are just verifying with the graph. On a problem like this, you may not be able to use your graphing calculator, and you would have to calculate it yourself. But it's nice for us to be able to check it here. Let's see what our second question is. What is the velocity and speed of the rock when it is 256 feet above the ground on the way up and on the way down? So let's think about what we need for part B. We are looking for the velocity and speed of the rock when it is 256 feet above the ground on the way up and on the way down. So we are looking for v of velocity, and we are looking for speed, and we need to remember that speed is the absolute value of velocity. So let's keep that in mind. So if we know the position, 256 feet above the ground, then we can calculate the times when we are at that position. So we'll start with that. We have 256 equals 160t minus 16t squared. Now we're going to solve this quadratic, so we'll move our 256 over and see if we can factor. I have factored out a negative 16, and we are left with t squared minus 10t plus 16, which will also factor nicely, so I'll continue with my factoring. Alright, factoring, we get negative 16 times t minus 8 times t minus 2. Using the zero product, we then set each of our factors equal to 0, and we get t equals 8 and t equals 2. So clearly, we are hitting 256 feet at t equals 2 on the way up, and at t equals 8 on the way down. We are looking for the velocity and speed at both of these times. So to get our velocity, we're going to plug 2 into our velocity function. And I'll do that and continue. Alright, so plugging in 2 and 8 into our velocity functions, we get 96 feet per second at t equals 2 and negative 96 feet per second at t equals 8. And we also were asked about the speed at these times, and the speed for both of these times would be the absolute value of their velocities, so it would be 96 feet per second for both t equals 2 and t equals 8. Alright, let's look at part C. Oops, too far. Sorry about that. Alright, what is the acceleration of the rock at any time t during its flight after the blast? Alright, so we are looking for the acceleration function, and we have talked about acceleration being the second derivative of the position function, or you can consider it to be the first derivative of the velocity function. So we are going to take one more derivative here. Velocity was 160 minus 32t. Give me a second to write that. And now we will take the derivative of that function to get our acceleration function. And the answer should make sense to us. The derivative of 160 minus 32t would just be negative 32. That would be feet per second squared. And that is the effect of gravity. Acceleration due to gravity is the acceleration at any time t in this problem. Our final part of this problem, if I scroll back up, we can see part D says, when does the rock hit the ground? Well, the rock hits the ground when the position is 0. And the position is 0 when we start, over here at time 0, and we are going to calculate when it hits the ground over here, which looks like 10 based on our graph, but we're going to do this analytically. So our s of t function, I'll write out and set equal to 0. Alright, and then we continue with factoring. We factor out a 16t. We are left with 10 minus t in parentheses, so we have 16t times 10 minus t equals 0. We use our 0 product, and we find that the height is 0 at time t equals 0 and t equals 10. So at 10 seconds, the rock will hit the ground. Alright, let's continue on. Okay, we have 2 explorations, and these actually I'm going to have you all do on Monday in class. This will be your class activity, Exploration 2 and Exploration 3. And now we'll take a quick look at Example 6, which is sensitivity to change. When this book talks about sensitivity to change, they are discussing whether a small change in x has a large impact on the change in y, or a small impact on the change in y. So let's look at this example. Here we have the Austrian monk Gregor Johann Mendel, working with garden peas and other plants, provided the first scientific explanation of hybridization. His careful records showed that if p, a number between 0 and 1, is the relative frequency of a gene for smooth skin in peas, which is the dominant gene, and 1 minus p is the relative frequency of the gene for wrinkled skin in peas, the recessive gene, then the proportion of smooth skin peas in the next generation will be given by y. So here we have y equals 2p times 1 minus p plus p squared, or y equals 2p minus p squared. And what we have below are the graphs of y with respect to p, and then the rate of change of y with respect to p, the derivative. So sensitivity to change would say, let's look at this first graph. If I can make it a little bigger. And let's look at what's happening when time is close to 0, or when p in this case, sorry, p is close to 0. If I move just a tiny bit to the right, I have a pretty significant change. And so when we are close to 0, this graph is very sensitive to change. Yet when we get closer to 1 up here, if I move to the right on the graph, just a little bit, say we were here, and we move just a little bit to the right there, we are less steep on our graph, so the graph is less sensitive to change because our y value is changing very little when we change our x. Back here when we were close to 0, we had a more significant change in y. So when we were closer to 0, our graph was more sensitive to change. And the way that you can interpret this with the velocity, the derivative graph, is the rate of change was far higher when we were close to 0. So on this graph, dy dp is equal to 2 when we are at 0, and very close to 2 when we are just to the right of 0. So that is a high sensitivity to change when we are close to 0, and a far lower sensitivity to change when we are close to 1, because our original graph became less steep. So when the graph is less steep, we have less sensitivity to change, and when the graph is more steep, we are more sensitive to change. All right, let's move forward. This is kind of interesting. It's not in every one of the calculus books I've taught us, but I thought it was pretty neat. Derivatives in economics. So engineers use the terms velocity and acceleration to refer to derivatives of functions describing motion. Economists, too, have specialized vocabulary for rates of change and derivatives, and they call them marginals. So they deal with cost, and so our dc dx would be a rate of change of cost with respect to x, and our cost function would be used to find our derivative. So we're doing the exact same thing that we've been doing with f of x plus h minus f of x all over h, but they're calling it a cost function. So they have c of x plus h minus c of x over h, and the limit as h goes to 0. This would be called the marginal cost of production. So in this case, x would be our production numbers. So this is the derivative of cost with respect to production. So let's take a look at an example dealing with economics. So suppose it costs c of x, so we have a cost function, x cubed minus 6x squared plus 15x dollars to produce x radiators when 8 to 10 radiators are produced. And that r of x, given by x cubed minus 3x squared plus 12x, gives a $1 revenue for selling x radiators. Your shop currently produces 10 radiators a day, so we are in the range to use the cost function that they've given us. Find the marginal cost and the marginal revenue. So let's use what we know about derivatives to apply this to an economics problem. So we saw in the previous slide that marginal cost was the derivative of cost with respect to production. So that's what we'll do here. We'll take the derivative of c of x, notated as c prime of x in this case, and using our power rules and our sum and difference rules, we get 3x squared minus 12x plus 15. And we are interested, let's see, it said your shop currently produces 10 radiators a day. So this is when x equals 10. So we'll just plug 10 in for x and get our marginal cost when we make 10 radiators a day. Plugging in our 10 into our derivative function, we get $195 for the marginal cost. Now we'll extrapolate If marginal cost was the derivative of the cost function with respect to production, the marginal revenue will be the derivative of the revenue function with respect to production. So we'll do the same thing with the R of X function to get our marginal revenue. Alright, so our marginal revenue would be the derivative of the revenue function, which came out to 3x squared minus 6x plus 12, and we're interested at x equals 10 radiators a day. So 3 times 10 squared minus 6 times 10 plus 12, giving us $252 for our marginal revenue. Alright, I believe that's as far as we have for this section. You were to work on the homework for this section, which was 1 through 23 odd, I believe, on page 135. And Monday in class, we will be talking about 3.4 and going over the 2 explorations. So I will see you on Monday.